Hello everybody. So in this video we're going to continue with chapter 11, Integral Calculus, and section 11.3, Areas. Okay, so we're going to start with example 11.13, which says find the area between the curve f of x equals x cubed minus x plus 1 and the x-axis over the interval -1, 2. So in these cases where the curve is above the x-axis, it's a very simple solution to find this area because all you have to do is a straightforward integration. So you would just integrate from -1 to 2 the whole function x cubed minus x plus 1. And this operation will give you the area that you see in blue here in this picture. So this is, again, a straightforward integration. All we have to do is use the power rule. So what we're going to get is x to the 4 over 4 minus x squared over 2, and then we have plus x, right? And then we integrate from -1 to 2, and that's just going to simply be plugging in the values, right, as we know. So we're going to get here 4 minus 2 plus 2, and this minus, we plug in -1, we're going to get 1/4 minus 1/2 minus 1. Yeah, and then this is going to give us 21/4. Okay, so here we are in example 11.14, and it says find the area under the curve f of x equals x cubed minus x minus 1 and the x-axis over the interval -1, 2. So this case is a little bit different from the previous one because we have a sector of the area here which is under the x-axis. So if we do a straightforward integration, we're going to get a negative result for this part. We would still get a positive result for this part, but the overall integration would be negative. Notice that the bottom area is larger than the top area, so we would get a wrong answer because we want the area in terms of a positive number. So that means that we would have to do two separate integrals, right? We would have to do actually the integration from -1 to 2 of the absolute value of f of x. But this would require us, if we do it manually, to find this point over here. And then we would say, let's call this point A. We would have to integrate, would say, okay, let's integrate from -1 to whatever A is, minus f of x. And then we would add from A to 2, just a simple integration of f of x. Now, why is that? Well, because remember that for the absolute value, if you're doing the absolute value of, say, c, that's going to have two solutions, right? It's going to be c if c is greater than 0. And it's going to be minus c if c is less than 0. So if it's negative, you have to put a negative in front of it in order to get a positive. That's what we're doing here. Okay, so the first thing we have to do is find this intersection. We would say, okay, x cubed minus x minus 1 is equal to 0. And notice that this does not have a straightforward solution. It does not have a simple solution that we can come up with on the top of our head. So we're going to actually use the GDC, and we're going to integrate the whole function from -1 to 2, but we're going to use the absolute value. So we would integrate from -1 to 2 the absolute value of x cubed minus x minus 1. So let's take a look at that. Okay, so here we are with the graphing display calculator. And for integrals, we need to use the math function here, and then option number 9, which is finite integration. So we click on number 9, and it takes us to this screen. So we said the interval is from -1 to 2. So remember that we have to type negative with this symbol here, -1 to 2. And then in order to get the right answer, we need the absolute value. And the absolute value you're going to find also by clicking on math, and then you move 1 to the right, And it's going to be the first option there that says as absolute value. So 1, and there we have the absolute value symbol. So now we just have to put in the function, which was x cubed minus x minus 1. And then we also have to put the symbol for x here to indicate that we're going to do the integration for x. And just click on enter. And there it is. Very well. So next we have example 11.15, and it says find the area enclosed by the graph of the function f of x equals x cubed minus 4x squared plus x plus 6 and the x-axis. So this is another case where you have a part of the graph that is in the positive side and a part of the graph that is in the negative side. The advantage we have in this picture is that we can see the x-intercepts. We can see that one is -1, the other one is 2, and we also have 3. We can test that in here, and using the remainder theorem, we'll see that they all give us 0. So how do we integrate this? Well, because we have a part of the area that is under the curve, we will have to think in terms of an area that would be equal to the integration from -1 to 3 of the absolute value of f of x. Now in this case, we can separate this into two different integrals. Why? Well, because from -1 to 2, we have a positive area, so we don't have to worry about that. That will be just a positive value. But from 2 to 3, we will have to do the absolute value, which is the same as saying minus f of x, right? Because it's in the negative side. So minus f of x. And this, right? So if we do this, and I'm going to continue up here, we would integrate then from -1 to 2 normally. So just for x cubed minus 4x squared plus x plus 6 dx. But from 2 to 3, when we integrate, we will have to use a negative sign in front of the whole function, right? So x cubed minus 4x squared plus x plus 6. And then integrate this. So notice that all these signs here will change, right? So for the first part, what we're going to get is, if we integrate that, it's going to be x to the 4 over 4. And then we're going to get minus 4x cubed over 3 plus x squared over 2 plus 6x. And then this from -1 to 2. And that we will have to add 2. And notice that this is going to change all the signs to the opposite, right? Plus negative x to the 4 over 4 plus 4x cubed over 3 minus x squared over 2 minus 6x. So notice that it's the opposite of the previous one. And then we integrate this from 2 to 3. And if you do the math, that's going to give you 45/4 for the first one plus 7/12, which is going to equal 71/6. So now we continue with example 11.16, and it says find the area of the region between the curves y equals x cubed and y equals x squared minus x on the interval 0, 1. So this is a case of area between curves. So when we have area between curves, what we'd have to do here is identify which curve is on top and which curve is on the bottom of this. So the top curve here, as you can see, this one, this curve, is y equals x cubed. And the bottom curve, of course, is going to be y equals x squared minus x. So the rule is when you want to find the area between curves, you have to integrate from a to b, whatever a and b are, top curve. So let's say if f of x is greater than g of x, then we would say, well, it's going to be the top curve f of x minus g of x. And this is what we would integrate. So in this case, the area would be given by the integration from 0 to 1 of the top curve again, which is x cubed, and the bottom curve, right? So the bottom curve is x squared minus x. And that's it. This is a pretty straightforward integration. Notice that this is going to equal x to the 4 over 4. And then we just have to be careful with the signs here. So it's going to be minus x cubed over 3. And then we're going to get plus x squared over 2. And then we integrate from 0 to 1. And if you do the math, this would give you 5/12. So next we have example 11.17, and it says find the area of the region bounded by the curves y equals x cubed plus 2x squared and y equals x squared plus 2x. So notice that they did us a little favor here by putting this area in a sort of reddish color and this one in green, which is an indication of that there has to be a different procedure for each area. Now, why is that? Well, because we said before that we have to do the integration of the top curve minus the bottom curve. So notice that here in this part, this top curve is y equals x cubed plus 2x squared. But after 0, 0, apparently, the situation inverts because you have the parabola on top of that, right? Notice that the parabola now is the one on top, y equals x squared plus 2x. So this would require two separate integrations. One from -2 to 0, apparently, and the other one would be from 0 to 1. So let's find out if these are the 3 points where these graphs intersect. So we would say x cubed plus 2x squared is equal to x squared plus 2x. And then of course this we can just rearrange. It's going to be x cubed plus x squared minus 2x is equal to 0. So notice that we can factor out x. So we get x times x squared plus x minus 2 is equal to 0. And then this is easy to factor because this is just going to be x times x plus 2 times x minus 1. So we confirm that the graphs intersect at x equals 0, x equals -2, and x equals 1, as we can see here. That means that we will have to do, again, the two integrations separately. So first we would say, okay, let's integrate from -2 to 0, top curve minus bottom curve. So top curve, x cubed plus 2x squared minus the bottom curve, x squared plus 2x. And to this we will have to add the integration from 0 to 1, and we flip the curves, right? Because now the top curve is going to be x squared plus 2x, and this minus x cubed plus 2x squared. Okay, so let's do the integration for the first one. Notice that then we would get x to the 4 over 4 plus x cubed over 3 minus x squared. And this is from -2 to 0. And then for the other one, we would get, okay, similar terms. So it would be minus x to the 4 over 4 minus x cubed over 3 plus x squared. And this will be from 0 to 1. Now you're going to notice something here. Notice that this here is exactly the opposite of this. So that means that if you do this in the graphing calculator, and we're going to test it in a bit, this would be the same as doing the absolute value. The absolute value. So you'd say integrate from -2 to 1, but do the absolute value of the top curve minus the bottom curve. So or either way around, right? We could say x cubed plus 2x squared, and then just minus x squared plus 2x and dx. And this would give us the same answer that we're getting through this manual method. But we'll verify this in a bit. So plug everything in here, and you would be getting 37 over 12. So now we're going to verify with the graphing calculator. Okay, so here we are with the GDC, and we're going to test the previous result using the fact that we can solve it with the absolute value in a straightforward manner. So click on Math, option number 9, where it says Finite Integration, and there's our integral. So we said we could integrate this whole thing from -2, so -2, and the upper limit would be, in this case, 1. But we said we have to do the absolute value. So for the absolute value, we click on Math, and then move 1 to the right. Under something that says num, we click on option 1, and there's your absolute value parenthesis. So we said we have to do the top curve minus the bottom curve, although with absolute value it doesn't really matter in which order you do it. X cubed plus 2x squared, that was the first curve, plus 2x squared, that was the first curve, minus, and here we have to be careful, use parentheses, the second curve, which is x squared plus 2x. And then we close parenthesis, and then we make sure that we're doing the integration in terms of the variable x. And let's click on enter. And notice that we get 3.08333 blah blah blah. Well, that is the same as what we found before, 37 over 12. So in the next slide, you're going to find an example of how to find areas along the y-axis. So here it talks about a case where you have to find the area that is enclosed by the curves y equals 1 minus x and y squared equals x plus 1. Now because this y is squared, it's probably easier to rearrange these and put them in terms of y, or x in terms of y. So notice that we could rewrite this as x is equal to 1 minus y, which would be this red line here. X equals 1 minus y. It was already indicated here. And then if we rearrange the other curve, it's obviously going to be that x is equal to y squared minus 1. So that's this inverse parabola here. This is the curve, x equals y squared minus 1. So then we would proceed in the same way, but we would do the integration in terms of y. And here what you do is that you subtract the left-hand side curve from the right-hand side curve. So notice that you can see here the integration from -2 to 1. And because it's in terms of y, right? So that's what you have to be careful with. So it's from -2 to 1 of the right-hand side curve, 1 minus y, minus the left-hand side curve. And don't forget to do the absolute value of that, absolute value, dy. Okay, so in this case, you would get 9/2. But the procedure is just the same. The only thing you have to be careful with is remembering that the interval is in terms of y, And then it's subtracting the right-hand side curve minus the left-hand side curve.